Okay, so we are in, what book are we in? Generalized linear models with examples in R. We're in chapter 2 and we're on question number 13 right here, which has many parts, 9 parts. So we'll go through them one at a time. But what applies to all of them is this kind of top part here. So a study exposed sleeping people, males and females, of various ages to 4 different fire cues: a crackling noise, a shuffling noise, a flickering light, and an unpleasant smell, and then recorded the response time in seconds for the people to wake up. Used a partially complete ANOVA table, table 2.7, which I've reproduced right here, to answer the following questions. Okay, so let's look at this table just a little bit here. So they say it's partially complete. And that could mean a lot of things. I hope that they are not excluding predictor variables. I don't think that they are. We could have a column here for the F statistic as well as the P value, and we don't have those here, but we will actually figure those later. And also notice that the degrees of freedom are missing for Q and for sex. Okay, and so our first question here is to determine the degrees of freedom for these 2 question marks here. Okay. Well, to do that, we want to go up to the different sexes here. So there's 2. All right. So our formula for degrees of freedom is the number of levels minus 1. So we have 1 degree of freedom for sex. And then we have 4 different cues: a crackling noise, a shuffling noise, a flickering light, and an unpleasant smell. So we have 4. 4 minus 1 is 3, and that's our formula for the degrees of freedom for the Q. And so this will be 3 and 1 here. Okay. Next is we want to determine how many observations were used in the analysis. Okay. Well, the way that we determine degrees of total freedom, or the total degrees of freedom, is the number of observations minus 1. Well, here we know the total degrees of freedom, and so we just have to add 1 to get number of observations. So how many do we have? Well, we have 60 plus 3, and then we determine that we have another 1 and 3 here, right? So we have 63, 64, 65, 66, 67, plus 1 is 68, okay? So I have 68 degrees of not degrees of freedom, number of observations. Okay. Now we want to find an unbiased estimator of the variance. Okay. So that is just simply, this is just the mean square of the residual. So it's the sum of squares residual divided by the degrees of freedom for the residual, right? And again, we can find those here. Right? So we divide this by this, and we get this. Okay. Now we're supposed to determine which explanatory variables are significantly significant for predicting response time using sequential F tests. Okay, so I write a little bit here, but basically what I'm saying is I don't really like this question because with sequential F tests, the way that it is explained in the book, there's too many combinations, or I mean, not too many, more than I want to do anyway. But there's too many sequences that we could run through these different variables here. And so I didn't want to do that. That would just be too much time. So instead, I'm just doing a non-sequential F test, or calculating the F statistics for non-sequential F tests. So I hope that's okay with you. So we go through here. Okay, so we have so for each of these, we have our mean square. Okay, so that's just the sum of squared divided by the degrees of freedom. Okay, and now our F statistic is basically the mean square divided by the residual mean square for each of these. And that gives us our F statistic, or our F ratio. And then we can use a bit of code, or use an online calculator, or go to a F table to find the P values, and that's what I've done here. Okay. One of the reasons that doing a sequential F test here, I think, would just be way too much work to get the lesson out of it. is because depending on the order that you do these, your residual will change, right? So if I was just going to do Q, well then the sum of squares from sex and age would have to be added to the residual because that variance will still be there in the data. And then I would have to calculate, the degrees of freedom for that new residual term, right? So in other words, there's just so many combinations to this that I did not do the sequential tests. Okay. Now, number 5 is the analyzed data is for participants who. The analyzed data are for participants who actually woke during the experiment, right? So again, remember, during the experiment, they're trying to see what makes people wake up. Some of these people did not wake up, and they were omitted from the analysis. How should this affect the interpretation of the results? Okay, so I've written a little bit here, and you can read it, or you might have a slightly different answer, and that's fine. But basically, that very much limits the applicability of the findings, because now everything is based on given that you wake up, ... okay? Rather than these things will make you wake up, okay? So really the applicability becomes not very, the applicability becomes very limited. So on the condition that you wake up, the analysis holds, or, may apply. If you did not, but it does not speak to the probability of you waking up, or the likelihood of you waking up. So, all right. Now, parts 6, 7, and 8 are having us look at different fits of our models here. Okay, so so what do I mean by models here? So we could look at our models. We could look at a model that's composed of all the explanatory variables, or just a subset of the variables. Okay. And you could make more combinations here, right? So the reason I didn't do the sequential F tests was because there's just too many sequences that you can do this in, and there's more combinations of predictor variables that you could put in here that I'm not doing because, again, I think it's more work than is required to get the lesson here. Okay. So in the first one, we want to calculate the AIC and then talk about what's suggested by the AIC. So in the book gives a formula for AIC that is specific to sum of squares, right? There's a more general formula that doesn't necessarily require the sum of squares, but that's okay because we have sum of squares. Okay, so this is the formula for AIC, right? So it's n times the natural log of the residual sum of squares divided by n plus 2p prime, or the numbers of parameters. How many parameters do we have here? Well, we have 1, 2, 3, and then we actually have an intercept. I believe that somewhere we're told that we have an intercept. If not, I'm acting as though we have an intercept. So, okay. So here's the formula, and all I'm doing is I'm just plugging in the values here. So I won't bore you with the math. You can look at the math yourself, and I've even reproduced the math or used R as a calculator here. And so hopefully I haven't made an error. If I have, hopefully you'll let me know. But the end result here is the AIC values. And remember that the AIC values, they don't mean anything in and of themselves. We can only use the AIC values to compare models that have been trained on the same data. And in that case, the lower the value, the better. So here, the full model is apparently better than the other models. Although they're all pretty similar, the one that really does the worst, probably appreciably does the worst, is just the intercept only. So in other words, no predictor variables, right? Okay. Now for what was that? That was part 6. So for part 7, we are using BIC, right, which is just I believe it's called the Bayesian information criteria, although it's not strictly Bayesian. I'm not really sure how it gets that name, but no matter. So we have a slightly different formula here. Okay, and you can find this formula in the book. It's equation 2.36. Again, I won't bore you with the math, but you can go through and calculate all that, and you these numbers here. Okay, and again, the full model probably is doing the best here. Something I should mention in both of these instances. Notice that the numerator here is RSS. And when we have the full complement of predictor variables, well, then the residual sum of squares is the residual sum of squares. But if I'm going to omit here in the second model, here I'm omitting age. Again, the variability in age is still in the model, right? So this this sum of squares is still present in the data. And now because we're not controlling for age, it is part of the residual sum of squares, and so too are the degrees of freedom and so on. So anyway, so you'll notice that pattern as you go through for that as well as for the BIC calculations. Okay. Final two. So we're going to compute r squared as well as the adjusted r squared, which goes by r bar squared. So if you're looking at this on the Colab sheet, right, if I zoom out, you'll notice that the bar sometimes is maybe a little bit hard to see. But anyway, so here's our formulas for r squared and the adjusted r squared. Okay, and so how are they different? So for r squared, the formula that I'm using is this one, mostly because it rhymes the most with one of the formulas for adjusted r squared. It rhymes the most with this one right here, right? So what's the difference between r squared and adjusted r squared? Well, adjusted r squared is r squared, but trying to find a way to penalize the model for the number of parameters, right? So just as in BIC and AIC, where we have a penalty term of either 2p prime or p prime times natural log of n, by accounting for the number of parameters you have in your model, you are effectively imposing a penalty for more parameters. And so only if you add a parameter to your model, only if it pays off in reducing the residual sum of squares, will that model perform better than a simpler model with fewer parameters. So anyway, so again, I've just gone through and done these calculations. As I go from more complex to less complex models, right? Notice how the omitted predictor variable is now part of the residual sum of squares. Okay, and p prime is also changing as I omit predictor variables. Okay. And so here we have all of the numbers. Again, I've done these in R, so you can kind of see how that looks there. So anyway, so what do we see here? We see once again that the complete model is doing the best, and then there's a pretty steep drop off after the complete model. So anyway, compare the model suggested from the ANOVA table. As per AIC, BIC, R squared, and adjusted R squared. Okay, so across all three models, we see that the complete model is performing the best in each instance, which is probably a strong indication that the full model is probably superior. And I guess that's it. I mean, I guess you could find some more similarities or differences between them, but I think that's maybe the important point here. Okay, that is it. Thanks.